Okay, well, welcome everyone. Can everybody hear me all right? So nice and loud. Okay, great. So everyone enjoying the event so far? Having a good time? Yeah, great. So welcome to our session today. In this session, we're going to be focusing on what it is to build a network that's ready for AI. And we like to term it as the network for AI networking. Specifically, we'll be calling out how we're working with customers today and leveraging our Cisco 8000 series platform, which is based on Silicon One. So just a little bit of a housekeeping first. In terms of if you want to have a further conversation after this session with Ruben or myself, you could either reach out to us directly to schedule a session, or you can go through the WebEx app. So if you haven't downloaded it yet, I do recommend downloading the WebEx app, and you should already be part of a WebEx space that's specific for the session itself. Okay. And just to quickly introduce myself and my colleague. So my name is Rob Piasecki. I've been with Cisco for over 17 years, and specifically working in the services side of the house. My current role is as a principal architect in the CX Services Product Management Group, working with service provider and web scale customers. Ruben?
Hey, my name is Ruben. It's a pleasure to be here. Quite excited to share with you guys what we are working on with our customers. My name is Ruben Fonte. I am CCIE. I am CCDE as well. I've been working for web customers, and I have been working for Cisco almost 4 years now, and it's a pleasure to be here with you guys.
Okay. Thanks, Ruben. So quickly, we'll just step through the agenda. I'll kick it off by giving an introduction into what are the trends and what's really driving AI capabilities for our IP backbone networks. And then I'll hand it off to Ruben, who's going to go through and specifically talk about what are the AI requirements, not just within a data center environment, but also traversing over an IP backbone or transport as well. He'll also touch upon what challenges that you can see and what we've observed working with customers, but then also how we solve those challenges and how we designed around them as well. So we'll go through examples of actual configurations of what we built in these AI networks, but then also we're going to step through and provide what is the troubleshooting that's unique to an AI network as well. And then we'll wrap up the session. So to kick things off, the AI revolution is well underway. So I'm sure everybody in this room has already been using some form of AI, whether it's ChatGPT or purpose-built AI agents that you may be leveraging within your environments today. So with this revolution, what we're seeing is that the rate of expansion of AI is at an unprecedented rate, much faster than we've ever seen before. And so with that, what we're seeing organizations see what the value of AI is to their business, and so they're already quickly adopting AI. So we see more than 2/3 of customers today already regularly using some form of AI within their network environments. This has forced us to really rethink how we design and build out these networks with these unique requirements, to the point that we're looking at more distributed architectures for these AI workloads. We're taking into account the unique requirements that AI may have. For instance, it can be, in many cases, a low latency requirement in your network, but also you have to take into account the capacity in terms of bandwidth as well. And we're building out these networks today together with service providers and other customers. And we're not just building it for today's requirements, but also what are the future requirements as well that AI is going to be driving. So what we're anticipating is that we're going to have exponential growth year over year for quite some time. To put things into a little bit of context, some measurements that we currently see with AI traffic in terms of capacity growth is what we're seeing is year over year growing upwards of 36 times what it may be today. Additionally, what's driving that bandwidth growth is that we're implementing new AI models and more complex models that are increasing in transaction size. So that transaction size is driving the bandwidth growth. And additionally, as we move to agentic frameworks and leverage more agents within our network, we're seeing increased transactions and communication among the agents themselves, including leveraging the data models that we're building around that. And so this brings a challenge to service provider networks. What we're going to specifically be focusing on here, Ruben's going to take us through, is this first box that's highlighted, really focusing on what are the requirements for an AI-based network, how do we design it, how do we build it, what's the configuration look like, and also how do we troubleshoot it, how do we operationalize this network. Service providers are continuing to evolve, also from a service delivery perspective, meaning that they're with AI-based workloads, they are, in many cases, very latency sensitive. And so what we have to do is we take that services edge that typically may be a centralized location within your network, and now we're moving that edge closer to the end customers. And so what we're seeing is edge services being terminated within like metro networks, which are much closer to the end user itself. And then, of course, energy consumption is always a core requirement, which is why we continue to evolve our routing silicon, so Silicon One, to be efficient without sacrificing the performance as well. So with that, let me hand it off to Ruben to start going into more details.
Let's go over a little bit about the requirements. Which kind of requirements have been receiving from customers? All the configurations, troubleshooting that we are going to share here is real use cases that we have customers already that have this solution in place. They are quite encouraging us to keep involving that. I'm going to talk a lot about it. But more focus here is about how web scalers are moving to the communication between DCs. Nowadays, this kind of situation is already common. We have already the DCs. We must have the interconnection between DCs. This is not quite new. But the new requirement here is how can I insert AI in this kind of environment? In the past, we have like 10,000 GPUs, 20,000 of GPUs. But the requirements start to come to us. I wanted to scale to 100K. I wanted to have 200K GPUs. And with this kind of requirement, it's not possible to have just one DC. We must have this communication from AI happening between DCs in order to fulfill all the expectations of AI. Again, this is every time is related customer requirement. All the requirements that we're receiving today, we are going to talk about the technology in the next slides. Pretty important here to understand that in the DC environment, in general, we have been working with this technology that I'm going to talk later. It's not quite new for DC perspective. What has been more and more common right now is this kind of requirements comes to aggregation layer in order to make this happen. From the AI workloads perspective, more and more we have been working, trying to make the communications between 100 kilometers. We have some customers that are asking us 1,000 kilometers. So it's something that we are still working on, but the majority of the case that's new for everyone here from the AI workloads is the aggregation layer. You are going to see a lot of, in the other presentation about DC, this is not quite new. This has been for at least 2 or 3 or 10 years now. But from aggregation perspective, this kind of requirements start to be really, really common to us. For example, high throughput, over 50 gigabits per second, low latency, milliseconds of the communication. And most important here that I wanted to emphasize, lossless. This is something quite new for us from the backbone perspective. I'm going through how we are going to provide lossless in the backbone. And after that, we are going to move in the communication itself. How can I have high throughput and low latency? Have you already here heard about RDMA? OK. Everyone here is from service provider? Enterprise? OK. So it's going to be more and more common to you guys. You are going to understand here why this technology is so important nowadays. how we are going to fulfill this expectation about RDMA. Why RDMA is so important for AI? We can achieve higher throughput, low latency, mainly because I'm skipping the kernel. I'm not burning CPU for this kind of communication. RDMA has the capability to go direct to the memory without any kind of interaction with the kernel. We are going to understand here how important it is in order just to skipping the kernel. From the DC environment, just because I'm skipping the kernel, I can save a lot of power. This is a unique benefit for them. That's the reason that this solution is becoming more and more common in the network, just because already provide power savings. But this is not enough for them. They need high throughput. They need low latency. And because it's not burning CPU, this kind of low latency and high throughput is possible. We did some tests with customers that RDMA, the comparison over TCP and over RDMA. Over TCP per hop, we have between 25 microseconds and 30 microseconds. From the RDMA solution, we have between 1 and 2 microseconds. You can see the difference between latency. AI requirements, we are talking about 10 microseconds per hop. So TCP is almost out of here, the requirements, because it's the best that we could achieve. It was between 25 and 30 microseconds. So we are going to talk here more and more about RDMA. All of you must understand how good is this, just because it's not the burning CPU is provide low latency and high throughput. Which kind of technology we are talking about? Why, in the past, if RDMA does not have any kind of ramp-up? RDMA in the past, until 2 years from now, it was mainly based on InfiniBand network. This InfiniBand network is standalone. It's just few vendors that can provide this one. There is no interop in the actual DC. So whatever is the DC, the technology that they have today, they are not able to interop. That's the reason from InfiniBand perspective, they are not able to have any kind of scale for the GPU's perspective. One point that's really important to understand from RDMA over InfiniBand, in the layer 2 of the InfiniBand, we can see that there is a credit-based solution that can avoid any kind of packet drops in the network. Because I'm not having any kind of packet drops in the network, I am fulfilling the RDMA expectation. So we are going to see the next slides that Rocky V2, the version number 1, it was not able to scale because it's just one broadcast domain. It was not able to scale to routing perspective. But the Rocky V2, we are going to see in the next slides that with the Rocky V2, we are able to scale as much as you can. Let's take a look here about Rocky. Rocky became more and more common. You guys that never heard about RDMA, you are going to be common more and more in the next 2 years about Rocky V2. This solution is becoming common for our customers, web scaler. They already have in place this solution. It's still working. We already have interop. And all the requirements related to latency and throughput we got with this solution. Rocky version 1, we are going to see the next slide. You can see there is no IP header. What mean? I cannot have a routing on that. So I cannot scale. It's not possible to scale. With the Rocky V2, I have this capability, and we're going to see the ramp up that's going on since 2024. Before 2024, we could see the InfiniBand, it was the dominant of the network. What is the constraint on that? There is no competition. There is any kind of interop. How the web is going to grow from TCO perspective if they have just a standalone network. It's quite impossible to grow in the cost perspective. Based on Rocky V2, why is Rocky V2 becoming more and more common right now? And the trend is going to be on Rocky V2. Because the cost efficiency, as soon as I have the majority of the vendor already support Ethernet, it's not quite new. Ethernet has been a long time here. And not just that, from the competition perspective, and interop, because in web they have at least 2 or 3 vendors, is a key for them, right? And not just that, from troubleshooting perspective, is a must, right? Everyone is aware how Ethernet works. Really key part here to you guys to understand that. How can I achieve losses? Losses is totally new for us. It's something that we have not been doing in the backbone. Now, how can I do that? So inside of InfiniBand, we have the credit-based solution. But in the Ethernet, we don't. How we can provide the same behavior of InfiniBand? We have the priority based flow control, PFC. This solution, this standard, can provide us a priority-based control that can avoid any kind of packet loss in my network. We are going to see step by step how it's going to work. But it's really important to troubleshooting perspective, design perspective, how PFC works. You're going to see in that part, I have here 2 switches, and one switch detects congestion here. The buffers start to fill up. And because of this buffer start to fill up, the PFC is sending down the notification in order to stop the communication, and then the result of that, the congestion is gone. So far, so good. I have the solution in InfiniBand. I have the solution similar in Ethernet. Perfect, I have the solution. Everything is ready to go to a real network. It's not like that. I'd like to provide you an example here. I have H1, H2, and H3 sending packets to R. Take a look in the point number 1, 2, 3, and 4. As soon as the detection in the R, switch R, detect any kind of congestion in the network, the action the PFC is, the port number 1, 2, and 3, is going to send notification to pause the frame. But take a look here in the point number 4. The S is sending packet to D. It's nothing related to the congestion. But because PFC is per port based, he's going to pause frames in both flows. So in the scale perspective, this solution doesn't work. We cannot scale with this solution. What's the solution for that? DistrictQCN. DistrictQCN is a solution per flow based. And in this scenario here, I'm going to be able just to impact the H1 and not the S. I'm going to cover this in the next slide. DistrictQCN with ECN. We are going to use ECN for notification, whatever is the congestion that I have in my network. I'm going to send the congestion point. I'm going to send a notification to notification point, and this notification point is going to send to the source the congestion it was identified, and the source is going to send the lower traffic. Pay attention on that, the difference between both. PFC is going to pause. But from the ECN perspective, we are going to decrease the throughput. I'm not going to pause at all. So with this solution, I can scale as much as I can. I don't have any issue about flow, and I'm not going to pause. I'm going to keep having traffic, but with lower throughput. Let's use this WRAD here. From the solution overall that I'm going to cover the configuration, we are going to use WRAD in our class of service. We are going to set the minimum and the maximum threshold in order to be able to achieve the expectation. What is the expectation from AI? Between 80 or 90% of my scenarios in the network, we must have a clear understanding about my memory, because the expectation is 90% of my traffic should be handled by ECN. PFC is my last resource, because if I'm going to have PFC pause frames, what's going to happen with the search? It's going to pause at all. I don't want to pause. I want the traffic keeping going. From the design perspective that you guys must pay attention is, we must understand the threshold that we're going to configure for ECN And from between the 80 or 90% of our burst should be handled by ECN. Let's put together both. Between the expectation to the design, we must have a clear understanding about our networks. It's key from our network to understand our burst. If you are not able to understand your burst, you are never going to achieve this case, because your burst is going to fill up, and then the pause frame is going to be sent. You must understand your network in such a way that your burst is going to stop in this level. We must have a clear understanding of the design in order to have a successful network for AI. You must be sure that that burst is going to be between WRAD min and WRAD maximum. If as soon as covered, as I mentioned, this is the last resource, we have the pause. I'm going to avoid at all the packet drop. But my throughput is not going to have as I expected to. So really important to understand here. I'm going to cover a little bit about how to configure that, but it's really, really important to you guys to understand from the design perspective how to keep between 80 or 90% of your burst in the WRAD max. Let's understand a little bit how is it working in the real network. I have my host A, B, and X, my leaf 1, 2, and X, and my super spine 1. Between now, I'm sending traffic without an issue. So far, so good. My network is working as expected. I did all my design in the perfect way. But I have the congestion. Leaf X detects some congestion. The buffer starts to fill up. And on that point, leaf X send the packet to host X that I got congestion in my network. Please send to the receiver point that I should decrease my throughput. As soon as host X receives this notification, a CNP packet is going to be sent between LX, S1, L1, and L2. These packets, CNP packets, is always be set as high priority in order to be sure that this packet is going to be arriving the other side. As soon as even I send to the host A and host B that should decrease my throughput, it was not enough in that scenario because I didn't do the calculation as expected. What is the result of that? Leaf X, they cross the threshold of PFC, and after that, leaf X start to send PFC. Spine 1 is going to receive this PFC, is going to send down to L1 and L2, and L2 is going to send to host A and host B, and the mitigation is done. Realize here, the mitigation is done as my last research. I just want to provide you an example how it works. But the expectation from the design perspective, always try to keep the buffer and the burst between in the WRAD threshold. But in the case that you are going to have, we are crossing this threshold, we are going to have PFC in action. What is the solution for that? Let's take a look at some solution that we are providing to our customers. Again, this is just some real example that we are going to provide here. We have a bunch of solutions for each customers, but for now we are working on 2 web players, and this solution is based on this solution that we provide, which is 2 web players. DC, Rocky. Between this traffic of Rocky inside of the DC, we have already between 65 and 70% of our network. So it's not new. The new requirement is the aggregation layer. And how I'm going to achieve high throughput, low latency, and lossless, Rocky V2, and for lossless, I'm going to achieve with DCN, DCQCN with ECN. Just to talk about some routers that we are working on, always Spitfire with the HBM1. Here, I just wanted to provide some examples. All these 8818, 8808, and 8804 are routers that we are working on right now. We have already in place, in production, with a bunch of traffic already. So if you want to talk about it, more than happy to support you guys for your specific case. But here, the majority of the case that's being done until now is based on these 3 routers. Any questions so far? OK. That's a good question. In this kind of scenario, I covered before, in general, we are achieving the maximum at 100 kilometers in order to avoid any kind of high latency to receive this signaling the other side. Until now, the majority of our customers, we are using 100 kilometers in order to achieve the expectation to be sure that this packet that was sent from here is going to receive here in the right time. But the calculation from the PFC, you must understand we have a calculation in kilometers. For example, we have a half of megabytes assigned for each kilometer. And then I can do this count in order to be sure that if I have 100 kilometers, I should have 60 megabytes of PFC. I need to do this in my design. That's one thing that I emphasize that. Everything is related. I should consider this point as a key of my design perspective. But yeah, your question is, as soon as I have any kind of signaling here, how am I going to be sure that this one is going to receive on time? We are going to reserve PFC for that, OK? Some challenge. All the routers that we have been working has HBM. All of you guys already have QoS in our network. We are not going to create a brand new network. One thing that I'd like to call out here is you must take in consideration the HBM, because HBM has been assigned for QoS purpose, right? As soon as we are going to assign from the PFC as well, we must be sure that the allocation that we're going to do for AI, for PFC, is not going to impact at all your normal QoS that you have today. From this kind of scenario, we are going to have, I'm going to cover later the configuration, but we must be aware how much memory are you using now or you're going to use in your forecast for QoS purpose, because you have 8 gigabits per second in the HBM. You must be sure that you are going to assign properly bandwidth for PFC, that's AI, and non-PFC for normal QoS. You have voice in your network, we have control in your network. So we must be careful in order to assign, because this memory we are going to assign for AI in order to be sure that we are going to achieve the lossless. We must be sure that the amount of memory is the right one, because this is configuring hardware. I cannot change during the fly. I must reload the router because this allocation is in the hardware. 2 points here to emphasize. PFC, they operates per port. Is not per flow. This CQCN helps us in order to achieve the per flow based control. If you are going to translate the UI requirement, mainly is going to be like that. We must have a clear understanding about our ECN limits, work here between 80 and 90%, and then as I already shared with you about the amount of memory that I have here, I must take into account how many kilometers I have. So it's it's few things that we must take in consideration, but you cannot fail on that. Otherwise, what we are going to see in our network, a lot of PFC storm. Your DC is going to start to complain because every storage is going to pause, and you are not going to achieve high throughput in our network. So this is something that, for sure, we as Cisco, we can help you on the design perspective in order to achieve all the expectation from AI. Another challenge that I didn't share yet, load balancing. From the AI workloads, they have a very, very huge flows. We have like 10 gigabits, even more. In order to have a right load balancing, we need to take in consideration not just the port, because all the AI traffic, RDMA, is UDP 4791. What mean? If I wanted to do the load balancing, my IP source and destination is going to be the same, and the port is going to be the same. How am I going to do the load balancing here? We have the solution in order to fix this issue, in order to take in consideration the QPET-ID. QPET-ID is the flow that RDMA do between source and destination. And I'm going to take a look of this QPET-ID. I'm going to share the configuration layer. And based on this, I'm going to be able to have a right load balancing. This is a really important point. Otherwise, we're going to see our network, some links full, some links empty. This is really important to take in consideration from the load balancing perspective, since RDMA have very, very huge flows. Let's take a look a little bit about configurations. How I can configure PFC. As I mentioned before, this is quite simple. It's not, you're going to see the next slide. From the configuration perspective, it's not complex. The key part here is the design. We must have a clear understanding about how to assign the buffer for QoS, the buffer for PFC, and then as soon as you have this, everything is calculated as expected, this is going to be easy. How I can configure? Priority flow control, and I'm going to assign hardware model profile priority flow control. I need one important point here from the configuration perspective. I must to configure just RDMA in the slots, in the line card that I'm going to use that. If I have a backbone that do not have any kind of possibility to have RDMA traffic, we have some customer that we assign between 7 and 12 for RDMA, and the 1 to 6 for non-RDMA. Why? Because if I have traffic coming from my backbone, I don't need to burn my memory for unnecessary RDMA traffic that's not going to happen in this slot. It's really, really important from design perspective, the allocation of line card. Because if you're going to assign to all of them, you are going to lose resources in your router. Questions here? Okay. Really important this topic, otherwise you are going to have any kind of drops in your QoS, and your customer is going to start to complain about your QoS and about maybe as well from the non-QoS PFC traffic. You can choose whatever you want. You can assign 10%, 20%, 50% based on your requirement. Yeah, I mean, if you have for example, 50% of PFC traffic, you can configure the knob 50%. If it's really, really based on your requirement. For example, you should have some KPIs, how much memory you are using from QoS without AI. You should have some percentage there, like 20%, 30%. And based on that, we are going to assign for PFC. But this is a good question, and you must take in consideration. You should check first, from the PFC perspective, you should check your QoS, how much memory you are using in your QoS. That's one thing I've been emphasizing this a lot because the majority of success of the AI network is based on the design, because the configuration itself is quite simple.
And how big is the maximum of the buffer? How can we know it can traverse how much traffic?
I didn't get your question. How much from the HBM perspective?
How big is the buffer?
Yeah, the buffer is 8 gigabits. I have 8 gigabits. And this, based on your traffic, you should have some configuration like queue limit in your network in order to buffer your traffic in order to avoid drops. Based on all, we have some telemetry for that you can see how much from the HBM you are using in your QoS. I can provide you offline information, but for sure, you can take a look in your QoS, how much HBM your consumption. The total is 8 gigabits. And you can assign, for example, we have customers that we are using 40% of PFC. Some customers are using 50% of PFC. It really depends on the customer use case. Okay.
So basically, when we configure buffers, the memory is reserved for PFC, even we don't hit the limit, so it's not reusable.
Yes, it's not reusable. Because this is in the hardware. As soon as you allocate the buffer, allocate the memory, you must reload the router, and then this memory is going to be allocated in the hardware. You cannot use.
Like QoS profiles on the old switches?
No.
Because you have to reload that.
Yeah, I mean, no.
The same principle.
No, I mean, whatever is the allocation that you're going to do, you must reload the router. And after that, for example, if you're using 3 gigabits of HBM, you must reload. And you are keeping using your 3 gigabits, right? But if you cross 4, you're going to see drops. That's the reason that you must be careful how much you are going to allocate for HBM for AI. It really depends on the use case.
It's not dynamic.
The dynamic is the configuration, but you cannot, because this configuration from AI, remember that from lossless. Lossless, meaning I must avoid any drops in my network. I just can do that in the latency that AI expected, assign memory in hardware. I cannot, otherwise I'm going to have a huge latency in my network. That's the reason, that's the trade-off, right? I mean, we must allocate in the hardware, and if I'm gonna change something, I need to reload the hardware again. But this is not just Cisco, this is the standard solution because this is in hardware, right? We must understand the use case in order to do the allocation of the HBM. You're going to say something?
InfiniBand will have the same limitation, but
Yes.
will have exactly the same. There is a hardware resource.
Yes.
Basically, FCOE, how it was, then similar techniques are reused, but for AI, right?
But yeah, the same idea, yeah.
Coming back to Silicon One on the slice configuration, line cards, that different versions. What is there any best practice to interface to the, let's say, hosts which are using AI in order to maximize the resource? Let's say you're talking PCMP, for example. I mean, how to interconnect using PCMP or bundle in the same router, facing workloads.
That's a good question. In order to allocate, I have, for example, in the 36400 line card, we have NPU in all this interface. This NPU has 8 gigabytes, right? If I wanna, these 8 gigabytes maybe could not be enough for you because we are gonna use. What we need to do is we need to take in consideration these 4 gigabytes for me is not enough from the QoS purpose. What we need to do for the QoS, you need to assign a new line card, right? That it's something that we need to understand based on your throughput that you're expecting, your burst. And then we need to do some calculation which makes sense to have both in the same line card or not. Of course, if you have the possibility to keep in the same line card, is better because you don't need to buy a new one, right?
Looks like a great tip. Why so late 9 nodes?
Because we are doing the hardware allocation, it's quite like that. For example, I share with you that our customer, we have 2 customers here that are using that. We did the allocation from specific line cards that's just using PFC. And the other one, I have the backbone traffic, let's say like that. Depending on the use case. Some customers, they are going to use both because they don't have much traffic. For example, our customer, we have 76 terabits of capacity, and they are asking more, right? So it's something that really, really depends on the use case. How I can configure that point, right? If I wanted to assign some kind of PFC in my QoS, I need to assign ECN, right? How does it works? Nothing new here. We have the traffic class 3. I'm going to assign this traffic class 3 to my policy map in the outbound. And in the outbound, I'm going to configure my ECN. You can see here, the minimum threshold is 1 millisecond. You can configure in bytes if you want, but in order to be easy, we just provide the configuration in milliseconds, but it's up to you from the customer. And the maximum is 2 milliseconds. So the configuration itself is quite simple. We are not bringing nothing. The only difference between is because from PFC perspective, we must assign in hardware this amount of memory. This is the configuration about user-defined header in order to do load balancing. If your load balancing is not enough from the elephant flows that we have in the AI network, this is an option to use the queue parity. More and more, queue parity is becoming common because from an entropy perspective, the UDP port 4791 is the only one that it was assigned for traffic from the RDMA. This is not enough at all. We are still working to provide other solutions for now. That one, that the best that we got for now. But we are still working with our customer in order to achieve better utilization. Troubleshooting. During the topology here, I'm going just to provide you an explanation how I can check my PFC and how I can check ECN. ECN is not new. Everyone that is already familiar with QoS purpose already check the ECN, but the PFC is quite complex. We are going to check that. Sorry, you did some question in the past?
Yeah, on the hardware side, you are enabling the bandwidth reservation on a line card basis, right?
Yes.
But do you have any line card that multiple silicon or ASIC? And is it possible to basically do that reservation on a per NP basis rather than on the line card basis?
No, it's per line card.
But once you do the allocation, all the NPs on that line card, they are now using it, but
Yes.
it's like a two-step process. You basically do the reservation on the hardware level, and then you enable that feature on a per interface.
Yeah, but as soon as you configure in the line card, it's going to be 100%. For example, if you configure your line card and you just enable one interface, even that is going to be assigned. All the memory that you configured is going to be assigned. Even we are not going to use.
But on a line card, you have multiple HBMs then, right?
No, in the line card, you have per NPU, right?
Per NP,
Yes.
per HBM.
Yeah.
That configuration, so you are essentially saying that line card, all the ports, all the NPUs now have that, from all the HBMs, that reservations, whether you use it or not.
Yes. Yeah. That's the reason that we must be careful about it. Use it if you want. For example, if you have some case that if you, in all the distribution interface, you are going to use 20%, you must be really, really assertive in order to not allocate much. But yes, you're right. It's per line card. Even I have 3 NPUs there. Is
Likely based on the RDMA concept, but you end up using all the ports.
Yeah, it really depends on the use case. We have some customers that they are using, but in the end, they start to insert some QoS, and the QoS start to have some drops, and then we need to assign some line cards for that. But yeah, it depends on the case. Let's understand a little bit how I can check PFC in my network. With show control and NPU priority flow, I can see what was configured in my network. XOF, meaning this is my threshold here that I assign. As soon as I cross this threshold, I'm going to send pause frames to my source. This is my the red one here, meaning that my maximum capacity that I have, and this is the threshold. As soon as I cross 62 megabytes, I start to send pause frames. Even I'm sending pause frames, I have here like almost 15 megabytes available because as she asked, even you send pause frames, not meaning that it's going to pause at that moment. We need to send to the source, right? And this is going to take some time. We need to do some calculation from the kilometers perspective in order to be sure that as soon as I start to send, I'm going to have buffer enough to wait until the, yes?
Just trying to clarify my concept.
Sure.
WRED min and max, right?
Yes.
So concept of WRED is congestion avoidance, right? So you basically start dropping something. Question is if you drop something, which means that you've already suffered a loss. So your packets, right? They are also passing through. So if you drop it on WRED min, so between min and max.
No, we are not going to drop. From DCN, we are going to send a notification to the congestion.
So when it hits min, basically an ECN will be.
Yes. It's going to decrease the throughput. It's not going to drop. Yes.
So not the regular red.
Yes.
WRED basically.
Yeah, they are going just to send, and then in the end, the host is going to understand, and then is going to send a CNP packet. This is this CQCN.
That goes back to the set source.
Perfect. Yes. We are using WRED, but it's not WRED. Yeah.
Anything which is QoS is a disaster for AI.
We must be careful. Yeah.
And restart.
But that's one thing from our customer perspective. We got numbers from the burst, and based on the burst, we did a calculation in order to be sure that our burst is going to stop here.
Meaning, not the QoS hours, what the QoS is supposed to do at one point.
Yes.
When it drops traffic, whenever is a loss in the network of the AI
Yes.
cluster, then all the processing trading stops. There has to be restart.
Yes.
Imagine it's running for 3 days.
Yes, sir.
We had a couple of packets lost. Restart once again.
Yes.
So all the packets going to be dropped are those non-AI traffic.
Yeah, no AI traffic is going to, based on your configuration that I'm going to send here, we have already the configuration. This is the configuration. As soon as you assign 50%, if you are going to use more than 50%, we are going to have drops in the QoS, the normal QoS, because before AI, you have 8 gigabits, right? Maybe now you move to 4 gigabits, right? What's going to happen? You just have 4. If you cross this 4, we must be careful about, how to do that. But yes, if you cross this 4 gigabytes, you're going to have drops.
If we have enough bandwidth, then we
Yeah, you don't need if you have enough. That's one thing that's important about load balancing, because if you have the right load balancing, you're not going to use much. Yeah. Yes. Let's move here. Some other points, just from the troubleshooting perspective, really, really good in order to provide some knobs. From the high-level perspective, how can I check that? You can see in all your interfaces, if you are sending or receiving PFC, this should be something shows that you should do for capacity planning. If you have too much PFC, it's something that you must to rethink your network. It's not expected. You should handle your network based on ECN and not PFC. This is really important point. If I wanted to do some troubleshooting, this is the information that I'm using the buffer here, but I'm not crossing the threshold of my X off. So I didn't achieve yet. I'm using, but I didn't achieve my maximum. In the second one, in the interface 6023, I'm achieving the maximum, I'm crossing the threshold, yes, I am in congestion scenario. For more one that's really important here is about, in order to check, if your network will start to see a lot of PFC, we have a specific knob that you can take a look each 30 seconds if you're still using PFC. If you're still sending in this command here, you're going to see the pause percentage. What does it mean? For 100% the last minutes, 53% of my time, I was sending PFC packets. So half of my time, I have too much congestion here. If you check the historical, so in my last 5 minutes, I'm sending a lot of PFC. So something is wrong in my design. I need to take a look for capacity planning.
This is a streamable telemetry?
Yes, yes. More information just about how to check this information about PFC, sending, receiving, still something that you should take in consideration from the capacity planning perspective. And this is the ECN, as it was mentioned here. We are not having drops. I have the mark here. Yes.
So every NP that has there's a on-chip buffer which is per port, which is I think on a silicon one is 100 millisecond or something. What happens to that? What role that on-chip buffer is playing when you are basically playing for the PFC or the HDD?
No, from the PFC perspective, you're going to use 100% of the HBM. From the QS purpose, you can use that one. Because the allocation is in hardware, right? We are not going to use that for PFC.
Class, you are basically redirecting and queuing everything in the HBM.
Perfect.
And the rest of the classes, which is non.
Yes.
So,
Yes, but this is a shallow buffer, right? Yeah. But yes. What's next? I've been talking about here in a lot of scenarios, in a lot of challenges that we've been facing with our customers. We're still checking PFC is not the best solution that we should have in order to scale our network. We are still part of the Ultra Ethernet Summit from the Ultra Ethernet Consortium. We are checking some evolution from PFC because PFC, in order to keeping scale our traffic that we are expecting a lot, this is just the beginning. And we need to keep looking for improvements. And the PFC is something that nobody is happy. We have already, it's working, but we need to go beyond, right? And load balancing improvement as well is something that we're still working on in order to have more and more possible load balance technique in hardware in order to be sure that I'm not going to achieve the maximum capacity. We are more than happy to support you and to have some doubts in our world of solution. We have some AI stuff there. If you want to, please stop by, take a look. It's really nice from what we are doing at Cisco on AI perspective. That's it. Do not forget to all the surveys is really important to us. We are here to support you guys as a customer. Really important to us to hear from you about our quality, about us as a speaker. Thank you so much. It was a pleasure to be here with you guys. Yes?